Well, welcome back, everyone. In the previous lectures, I've been showing you the most commonly used method by epidemiologists to control for multiple confounders, a regression model. I've been trying to build a case that if you build a model, a valid model, a model built on valid assumptions, that shows the relationship between your exposure of interest and your confounders with your outcome, that you can focus on the coefficient of the exposure and interpret that coefficient as an adjusted measure of association, adjusting for the other factors in the model. That's the most commonly used method by epidemiologists to control for confounding. But there is an alternative. It's an alternative that's been around for many years. It's becoming more commonly used now than in the past, but still nowhere near as used as commonly as regression models. But I want to introduce it to you, so you'll be aware of this alternative method. It involves something called propensity scores. So the motivation is the same thing we had before. We have multiple confounders. We're going to be using that same example we had in the previous couple of lectures, looking at the effect of blood pressure medication on your odds of dying in 24 years of follow-up, controlling for 10 potential confounding factors. But now we're going to do it differently. Basically, we're going to create something called a propensity score. I'll show you what it is in a few seconds. And the motivation is we want to control for a large number of potential confounders like in the previous example. The way we're going to do that is to combine those 10 potential confounders into a single number, a single summary score. It's sort of like your ultimate confounder. That if you just control for that one summary score indirectly, you'll be controlling for each of the individual confounders that made up of that summary score. Well, first a little bit of history. Propensity scores were developed more than 30 years ago. I remember being a student here at the Harvard School of Public Health, studying for my doctorate, reading these papers that were written by a couple of statisticians from Harvard, from the Department of Statistics, about the theory behind propensity scores and how they might be used to control for multiple confounding factors. So those papers were written in the early 80s, 1980s, but the propensity score method wasn't used very much in the clinical and public health literature until the last 5 or 10 years. And now they have undergone a renaissance. They are being used a lot more now than they were in the years following their development, following the years in which those theoretical papers were written by the statisticians. Now, if you ask, why is our propensity scores more commonly used now in the recent past compared to the distant past? I think it's because of certain types of epidemiologists who are faced with the problem of multiple confounding factors have realized it's an alternative method to control for multiple confounders. Well, who are those researchers? Well, the pharmacoepidemiologists. And if you remember, a couple of weeks ago we had Alec Walker here, giving you a paper to read, a retrospective cohort study. And Alec began his lecture by telling you what he did. What he does. He is a pharmacoepidemiologist. He looks at the effects of drugs, the unanticipated effects of drugs. And in those studies, they use observational data set where they have potentially large number of confounders, because the indications for receiving a certain medication, like blood pressure medication in the previous example we looked at, might be driven by a number of factors, which are also risk factors for developing the outcome. So the pharmacoepidemiologist is often faced with this multiple confounding problem. There's another set of researchers called health services researchers who also have this problem, measuring the effects of certain clinical decisions to admit a person to a hospital or not, or to order a certain test or not, or do a certain procedure or not. And those decisions are driven by many factors, many indications, which are also risk factors for outcomes that they're interested in. So in both situations, the pharmacoepidemiologist and the health services researcher is faced with this multiple confounding situation. And propensity scores were developed for that particular problem. Well, what is a propensity score? Mathematically, it's nothing more than the probability of receiving the exposure, the treatment of interest. So in the previous example, we were looking at the effectiveness of antihypertension medication at the 1956 examination in your Framingham data set, BP Meds 1, on your chances of dying in the next 24 years of follow-up. What the propensity score is going to try to capture is how do doctors take into account all these other risk factors, like age and sex and blood pressure, histories of heart disease, when they decide to put a person on antihypertension medication or not put a person on antihypertension medication. So what the propensity score is trying to do is mathematically quantify how doctors think by coming up with an estimate of the probability that a person will receive a treatment based on the factors, based on these confounding factors. So in terms of the causal diagrams, and I'll show you the causal diagrams we had in our minds before, we wanted to know whether hypertension medication has an effect on whether someone dies or not. That's the whole purpose of the study. In the previous lecture, we talked about how do you control for confounding by factors like age and sex and blood pressure and diabetes and those other 6 factors that I had in Table 1. We were focusing on, in the regression model, in the effects of each of these factors, the exposure, hypertension medication, and the confounders on the outcome death. We were looking at the relationship between those factors and their effects on the outcome. Now we're going to switch gears. We're not even going to look at death at all for the time being. We're just going to focus on the connections between the confounders and the decision to treat or not. We're going to try to mathematically quantify how a person's age, sex, blood pressure, diabetes status, etc. influence the decision to put a person on hypertension medication or not. So propensity scores now are going to be looking at these red arrows, not linking the risk factors, not linking the confounders to the outcome, but now linking the confounders to the exposure, trying to quantify how do these risk factors, age, sex, blood pressure, etc., influence a person's doctor's choice of treating a person with hypertension or not with hypertension medication. So that's what the propensity score is trying to do. It's looking at the relationship between the confounders, not with the outcome, but with the exposure, a different direction, a different type of analysis. So let's suppose you took your Framingham data set. Let's suppose you fit a logistic regression model. We fit a logistic regression model in the previous example to look at the relationship between the exposure and the confounders with the outcome death. Now we're going to be looking at the relationship between the confounders with the exposure. So the propensity score is trying to estimate the probability of getting the treatment, the probability of being placed in the on medication group, the 139 people who received the antihypertension medication before their 1956 exam. We want to predict that probability based on the confounders only. So notice this logistic regression model contains terms for age and total cholesterol and systolic blood pressure and diabetes, all the factors that are in Table 1. It does not contain the outcome, death. So the model itself doesn't tell you anything about the relationship between your exposure, BP meds 1, being put on antihypertensive medication, and your outcome. What the model is trying to do is mimic, trying to reflect how doctors make the decision to put some people on hypertension medication and others not, by building a model where the outcome, the left-hand side of the equation, is not your log odds of dying, but your log odds of receiving the treatment. That's what the propensity score is trying to do. So once we have this fitted equation, I can take each of my people, each of my 1,300 people in my data set, plug their values in for age and cholesterol, systolic blood pressure, diastolic blood pressure, sex, smoking, etc. Plug in the values that each individual person has for these 10 different confounders. Add them up, weight them by their coefficients, and then add them up, I should say, and I'll get an estimate for that person's log odds of receiving the medication. I can turn that log odds into an odds. I can turn that odds into a risk. That's how I get the propensity score for each person. So the propensity score is a number that's assigned to each person, which is his or her estimated risk of getting the treatment being blood pressure medication. Okay, so that's the mechanism involved. Why do we do this? Because the propensity score, in theory, should be a balancing score. Meaning, if I look at people with similar values for the propensity scores as a separate stratum of people, and compare those people in that group who received hypertension medication to those who did not, I should see balance with respect to age, with respect to sex, with respect to blood pressure. If the propensity score works, if it really does capture how age and sex and blood pressure influences the choice of getting antihypertension medication, If I look at people, stratify, if I wish, by the propensity score within stratum and compare those people who actually got the antihypertension medication to those who did not, I should see balance, as if I had a randomized trial looking at me within that subgroup of people. Well, let me try to explain that with a couple of examples as following. First, let's suppose we leave propensity scores for a minute. Go back a few weeks ago and we talked about experimental studies, randomized controlled trials. Let's suppose you and a colleague of yours were going to do a multi-center randomized trial. You were going to do it at your institution and your friend was going to do it at his or her institution. When let's suppose that's in another part of the world or another part of your country. And you talked about how you're going to do this study, and both of you agreed we're going to do a randomized controlled trial. We're going to randomize people to receive a new treatment versus a standard of care treatment, or to receive a treatment versus a placebo. So you do the study at one site, your colleague does it at another site. Let's suppose site number 1 is your study. And what you're going to do to randomize people to receive a treatment or say to receive a placebo, T plus means you receive the treatment, T minus means you receive a placebo, is you flipped a coin. If the coin came up heads, you put that person in the treatment group. If the coin came up tails, you put that person in the non-treated group. Well, what would you expect in your study if you did this? Let's suppose you had 200 people enrolled in your site. You flip a coin for each of them. You would expect 100 of them to be put into the treatment group and 100 to be put into the non-treated group or the placebo group if the coin is fair. 50% chance of getting in the treated group, 50% chance of being in the non-treated group. Let's suppose among those 200 people, 60 of them were men. 30% of your data set was made up of men. Well, you would expect when you flip these coins for those 60 men, 30 of them would put in the treated group and 30 of them would put in the non-treated group. When you flipped it for the 140 women, 70 of them would put into the treated group, 70 in the placebo group. What would you expect? When you looked at the 100 people who were assigned to your treatment group, you'd expect half of the men, 30, to be there. You'd expect half of the other half of the men to be in the non-treated group. So what's your percentage of males in the two groups? It's 30% in one group, 30% in the other group. The coin flip gives you two balanced groups. What if you had the average age of everybody in your study was 40 years old? Some people were 60, some people were 20. On average, people were 40. When you flip the coin, just as many old people get put into one group as in another, just as many young people get put into one group as another. You would expect the average age of your treated group to be 40 years old. You'd expect the average age of your non-treated group to be 40 years old. That's the balance you'd expect in your randomized trial at your site. Well, before I go any further, what's the propensity score in your study? Remember, the propensity score is the probability of getting the treatment. You got a treatment. If the coin was flipped and it showed a heads, say that's one side of your coin. If it's a fair coin, the propensity score would have been 1/2. And the conclusion you'd have is no confounding because the two groups are balanced. Well, let's suppose we look at your colleague now who's doing this study at site number 2. And at site number 2, he is also using a random device to assign people to the treated or the non-treated group. But unknowns to you, he's not using a coin, he's rolling a die, a dice, one of the two, which is a 6-sided figure, a cube. Each side has an equal chance of facing the sky when you roll it on the floor. And let's suppose when he rolled his die, if it showed a 1, you were put into the treated group. If it showed a 2, 3, 4, 5, or 6, you were put into the placebo group. So there's a 1 out of 6 chance of a person being put into the treated group. Well, let's suppose he has 600 people enrolled in his study. Rolling a die, you'd expect 1 out of 6, 100 of them to be put into the treated group, the other 500 in the non-treated group. If he has in his group 60 men, 10% of his people in his 600 people are males. When he rolls the die for these 60 men, you'd expect 1/6 of them, or 10 of them, to be put into the treated group, and the other 5, 6, 50 of them to be put into the non-treated group. For the 540 females, you'd expect 1/6 of them to be put into the treated group, 5, 6 in the non-treated group. So what's the distribution of sex in his study? 10 out of 100, 10% of his treated people are men. 50 out of 500, 10% of his non-treated people are men. If his average age of everybody in his study is 60 years old, 1/6 of those people should be put into the treated group, equal numbers of old and young people. You'd expect the average age of everybody in his treated group and his untreated group to be 60-60. He'd expect balance also. Well, what is his propensity score? His propensity score is 1 out of 6. That's the chance of being put into the treated group. And again, he would conclude no confounding. So finally, when you finish your study and he finishes his study, you tend to combine them combine everybody into one table. So you take your 200 people along with his 600 people. You would do a study with 800 people. Now, how many of those 800 people are going to be receive the treatment? 100 from your study, 100 from his study. So 200 of those 800 would have received the treatment. How many would not receive the treatment? The remaining 600. What's the sex distribution of the 200 people in your total study among who received the treatment? Well, remember, there are 30 men from your study. There's another 10 men from his study, so 40 of those 200 treated people will be men. 40 over 200 is 20%. What's the sex distribution of the non-treated people in your entire study? You've got 100 non-treated people in your study, 500 from him, so you've got 600 altogether. You've got 30 men in your study who are non-treated. He's got 50 in his study who is non-treated. You got a grand total of 80. 80 out of the 600 people who are in the placebo and the non-treated group are men. That's 13%. So notice in this combined study, made up of 2 randomized studies where there was no confounding, where everything was balanced, suddenly sex is not balanced. The treated people have more men, 20%, compared to the non-treated people, 13%. So in this case, you say suddenly you have potential for confounding here. Well, what's happening here? If you stratify by study site, there's no confounding. If you combine them together, there is potential confounding by sex in this case. When you stratify by study site, you are essentially stratifying by the propensity score, meaning if you looked at people who had a common value for the propensity score, in this example, there would be no confounding. So stratifying by the propensity score seems to avoid confounding. Well, this isn't a randomized trial. Let's go back to the study we were talking about, an observational study where people are either receiving antihypertension medication or not. Let's suppose now we think about the confounding in that study. Again, remember your exposure is BP meds. Your outcome is death. Say we go back 2 slides and we build this propensity score. We build a model that predicts your chances of receiving blood pressure medications. Let's suppose we take each of our people in our data set and plug their values into this equation to estimate each individual's person's value, their predicted propensity score. Some people might have predicted propensity scores near 0. Some people might have predicted propensity scores near 1. Let's suppose I do the following. Let's suppose I look at propensity scores, which are, say, 0.6. And let's suppose I have 100 people. Each of them has a propensity score of 0.6. Now, there are different ways you can get that propensity score of 0.6, but let's suppose I had 100 people. I put their values into that equation from 2 slides ago, and 100 of them ended up having propensity scores equal to 0.6. Let's suppose I build a table only among these people, looking at the people who did receive blood pressure meds to people who did not receive blood pressure meds. And first of all, how many people do you expect out of these 100 would have received blood pressure medications if each of them had a 60% value for their propensity score? Remember, the propensity score is the probability of receiving blood pressure medications. Each person has a 60% chance of receiving a blood pressure medication. I would expect, in this case, then 60% or 60 of them to receive blood pressure medications and 40 of them not to receive blood pressure medications. That's what I expect first. Now let's suppose I look at, say, their average age. I take these 60 people Each of them has an age. I average those numbers together. Let's suppose what happens when I do that is that on average, these 60 people are old, while the 40 people who did not receive blood pressure medications are young. That means within this group of people who have a common value for a propensity score, 0.6, they're not balanced with respect to age. Age could be a confounder. That would be a problem. But if the propensity score is really doing what it's supposed to do, remember the propensity score is supposed to capture the influence of age on the decision-making process to put a person on medications or not. This tells me there's still some predictability left over. After I put people into groups with common propensity score, age is still a predictor. In this group, older people are more likely to get blood pressure medications, and younger people are less likely to get blood pressure medications. Things are not balanced. That means the propensity score didn't do its job. It didn't capture the true relationship, the influence that age has on the decision to give some people blood pressure medications and other people not. But if the propensity score really did do its job, then I would expect among people who receive blood pressure medications, if on average they were old, then among the people who did not receive blood pressure medications, on average they should be equally old. Because if the propensity score is capturing the influence of age on the decision to receive a blood pressure medication, there should be no leftover relationship between age and whether a person did or did not receive blood pressure medications. Similarly, if I looked at the percent of people who were males, I would expect that among the 60 people who received blood pressure medications, that if 40% of them were men, I would expect roughly 40% of the people in the other group who did not receive blood pressure medications to also be men. Otherwise, there would still be some predictability left over between sex now and the decision to receive or not receive a blood pressure medication, meaning the propensity score didn't do its job. So the theory says if the propensity score really works, if it really does capture all the relationship that these factors have on the decision to receive the treatment or not receive a treatment, if you group people by values of the propensity scores, as I have here, looking at people with a common value, then within that group there should be no leftover relationship between the individual confounders and the exposure, the treatment. That's the theory behind the propensity scores. In terms of a causal diagram, what it's trying to do is if I fix or condition on the propensity score, I should be removing the independent relationships between the confounders and the exposure. Meaning, if I go back to this picture, if I fix the value of the propensity score, there's no longer any relationship between these individual confounders and the exposure. So if the propensity score works, if it captures the total influence that age and sex and blood pressure and diabetes has on the decision to receive blood pressure medications, if I stratify by ranges or values of the propensity scores, I should see no leftover relationship between age or sex or blood pressure with the exposure. I blocked all those pathways. That's the theory behind the propensity scores. Okay, so that's the big picture. When we come back, I'd like to go through an analysis now using the blood pressure medications, repeat what we did before, not using a regression model, but use a propensity score analysis to try to control for confounding. So I'll see you then.